Hello. So in this video we will see what is the stack device and what are the things to be taken care while designing the stack devices or NMOS. Basically we'll see the NMOS only in this video. So what is the stack device and what are the things to be taken care. So first thing I want you to see from this snapshot that uh, if if let's say this is your total L, okay, this one I have marked this is your total L, okay. So what I did, I have made split this L, total L, in sub parts. So what I do, I'll make this L something like this, that one section is this and another section is this, okay. The tapered one is L2 and this is L1. And one more thing is, we will make L1 is equal to L2. So we will find the length which is tapered one, and this is the L1, okay. So total L is being split into different L such that other which one is the tapered is being separated, and others which are in a rectangular has been separated. Only condition is these L, this L1 should be equal to the L2. So if you see this, total L is equal to L1 plus L2. So we have split this, and if you see in a top view again, if I tell you in this way, okay. So what we can observe here, we can see that this is one device and this is the second device, okay. If you see closely the connection between the gate, so this is one device where this is source, this source is equal to this source, okay. This drain is equal to this drain, and gate is also made here same. Only thing is that we have separated this L1 and L2. Here is L1 and this is L2, okay. So we can see from here that this will be in a linear region and this will be in a saturation region, okay. So this is the way of visualizing how the complete L, total L is being the total L has been split into into different smaller L, such that the one which has the tapered L is been separated, and other are which are rectangular has been separated, and this is in the linear region, and this one was the in saturation region. So this L1 and L2 will make two devices, M1 and M2. So if we see here, what we will see that this device will be something like this, okay. I'll show you from here, you can see. So this device, this is first one and this is the second one. So this is gate, common gate has been connected, and this is one source, this is one drain, and this drain was connected to the source, okay. Similarly here, so So from here you can see if this is L and this is L. Okay, we will make, the condition is we will make L1 and L2 same. So this is L, then total L will be 2 times of L. Okay, so this is the stack device, and the upper one will be in a saturation and lower one will be in a linear. How it came? Because from the figure itself, if you can see that whichever the MOSFET, let's say whichever the MOSFET which is closer to the source will be in linear region. So this will be in linear region, and whichever is closer to the drain will become the saturation region. So this is one of the intuition method, or you can say that from the device physics we can see that which MOSFET is in a linear and which MOSFET is in a saturation region based on the L and based on the device physics, based on the actual structure of the MOSFET when connected in the stack. Okay, so only condition is that both the size, basically the W M of M1 and M2 and length of M1 and M2 should be make same. Okay, then this basically M1 and M2 are identical, then we can say that this condition, saturation and linear, will be there. Why it is so, I'll tell you in a different video that what will happen if we have a different let's say length L1 and L2 are different or width are different, then problem is there will be different VTH. Okay, so because of different VTH things will be different. So because VTH is also dependent upon the length of the device. Okay, so for now L1 and L2 are same, both two MOS, these two MOS, M2 and M1, both are identical, and this is the way of visualizing in term of device physics. Okay, now what we can do, let's go here, let's see if we have a this device. Let's see, we have M6, M5, M4, M3, M2, M1. There are 6 MOSFET that are connected in a stacked way. What is the stacked way? That the gate is common for all of them. Okay, and one drain is there and one source is there, and there the consecutive drain and source are connected. So in this way the total L will be 6 times of L. So what does it mean? That total L will be equal to 6 times of L. If let's say each length of the MOSFET is L, then total L from here to here will be 6 times of L. Okay, now we want to know which one will be the saturation and which one will be in the linear. From the visualizing the MOSFET in the series, we can see that something like this, that if there is a L, something length is of the MOSFET is something like this. So we have separated this, the tapered one, okay, which is closer to the drain, and separated the other one. Okay, and we have split this total L in such way that this the last one L, whatever it is, this is the individual MOSFET length is equal to L, has been made according to the such that this is the one MOSFET that is closer to the drain, has the length of this. So we split according to the this size. So we have splitted it accordingly. So all the other, if you see here, all this till here are in linear, all the MOSFETs, and this will be in a saturation. So this is the way of visualizing the stacked device, stacked NMOS with respect to the length set. Okay, going forward, now we will this is the way of visualizing in term of structure of the MOSFET. Now we will see in term of voltage. So before that I want you to visualize with respect to the what is the saturation condition of the device. Okay, so what is the saturation condition? What is the saturation condition of a device? So we know first thing is that this device has to be on. So this voltage drop should be, VGS should be greater than VT. What is VT? VT is the threshold voltage of the MOSFET. Okay, this is the primary condition that we already know. Okay, second thing is the voltage drop from gate to drain should be less than VT. So one is the first we know that VGS should be greater than VT. Similarly, this voltage VGD should be less than VT. So this you have to remember. Why it is so? Because if you see here, okay, there is no channel here. So for no channel, the voltage drop between gate and drain should be less than VT. So that is what VGD should be less than threshold voltage of the device. So this is same here. If you see, VGD is less than this voltage. This voltage VGD should be less than VT, and VGS is made greater than VT for working of the NMOS. Okay, and we also know that from the basics that for saturation condition VG should be greater than VTH. From here also we get this, that VGD should be less than VTH. So what is the summary here is that to keep in mind is that if we see closely is this, that this VGS should be greater than VTH and this VGD should be less than VTH threshold voltage basically. Okay, this is the saturation condition. Now for the stack device, let's go for the stack device. What is the voltage condition and voltage requirement? So first thing, if you see here closely, this is the stack device I have made. First MOSFET, okay, this is the M1, this is M2, this is gate voltage, this is drain, both gate are connected, and this source of M2 and source or drain of M1 is connected. Okay, now in term of voltage, first thing is that this has to be, M2 has to be on. Okay, when it is on, for the requirement is VGS2, this voltage has to be greater than VT, or this is same as this. So this voltage VGD also greater than VT, and we know we saw just before that for a MOSFET this voltage should be greater than VT and this voltage should be less than VT for the saturation. Okay, but here this VGD, this voltage is greater than VT if you see here. So this M1, the below one, will be in a linear region. Okay, so this is the visualizing with respect to the voltage, not with respect to the MOS structure, but with respect to the voltage, that that is easier to visualize. Why? Because this voltage VGD is greater than VT, and for saturation this should be less than VT. Okay. Now second thing is, now M1 is linear. For this whole device to be in saturation, only way is to become a saturation is to make this M2 to be in saturation region. Okay, so if we want to know that, let's say this device complete structure has been split, let's say this is two device and this is the equivalent device L, this is 2L. Okay, so we want this to be in saturation. So what I will see, that I'll see for the top MOS to be in saturation. Okay, so what does it mean? This means that gate drain, this drain should be greater than Vg minus Vt. This drain should be greater than Vg minus Vt. This is the condition. Okay, this drain should be greater than Vg minus Vt. Then only this complete thing will be in a saturation region. So top MOS should be looked for the saturation region of the complete stack device. And also when you want to see the margin, VDS margin for the saturation region, then also you have to look for this, that what is the VDS across this, what is the VDS across this minus what is the VDS minimum, that is the margin available here. Okay, similarly for the overdrive or the gate margin, gate VGS margin, what should we look? So it's very simple here, I'll show you. So here also if you see, this is the gate and this voltage, let's say this VA is equal to VB and VC. Okay, A is equal to B plus C in term of voltage. Okay, this voltage total is equal to this voltage plus this voltage. Okay, so obviously this MOSFET, the lower one MOSFET M1 has a higher VGS. So if we need this voltage, if we want to give some voltage here, then the primary thing to be looked, which MOSFET has to be looked for the designing, is the lower one. Because if we satisfy the lower VGS, already we will satisfy the VGS requirement for this M2, the top one. So input voltage should be greater than the VGS lower one. Okay, then it will automatically will be greater than the top VGS. Okay, so for the margin at the input, we will take the VGS of the lower device. So VGS of the lower device will be considered for the margin calculation. Okay, so overdrive margin or whatever margin you say in term of V input, that what is the V input above VTH you will take. So for that you will take the VGS of the lower MOSFET and you will subtract it with the VTH and you will see the available margin available for that. So this is the with respect to the device, with respect to the voltages, that how MOSFET stack device will look upon. So yeah, that's it. Thank you.